So what I thought I'd do for this lecture is talk about first the current conditions we face, last year being the hottest year on record, and the predictions being that this year will either be the hottest or second hottest on record. And does this really mark a change in what's happening with our climate system or not? And this is a sort of overriding question that I'll sort of be talking about. But when I put the title of the paper together and submitted it the first time, these things never are straightforward. At 1.5, prior to that, the temperatures were about 1.3 or 1.2 degrees. So when I was suggesting 1.5, it was kind of semi-outrageous. But then in the process of reviews, the temperature did the following. So in 2023, this shows this black line here, and these are the months along here. And actually, this scale is absolute temperature. So you see the northern hemisphere in July is the warmest. That dominates the global record. And there is this black line is way above any other measured year by quite a long way in temperature. And you can see it's almost almost a degree. Well, it's a degree above half a degree above the previous one. But if you took the average, it's almost a degree above the average temperatures across all the months. And this led this guy who heads NASA. They have some of the best data collections, and they're the experts. And in Nature, he wrote, if this does not stabilise by August 24, he's talking about, a reasonable expectation based on previous El Nino events, which I'll show you later, then the world will be in uncharted territory. By that he means the climate system is changing or about to change in a way we probably can't fully understand or predict, except look at these observations in hindsight. I'll just explain that. Another word for that is tipping point, a change in how the system itself is operating. It could imply that the warming planet has fundamentally altered how the climate system operates, and it's much sooner than scientists had expected. Well, now here's the update for this year, 2024. I just downloaded it from the latest Berkeley Earth. That's another very useful site. In this case, we're talking about anomalies, right? So you'll see I'll be talking all about anomalies, so it's important you follow what the anomaly is referenced to. So each of these anomalies is referenced to that month. So it flattens out the line. You no longer see the seasonal change on the Earth. It's a straight line, but here is now 23 is in red, right? And now our 24 is in black. And it looks like it's marching slightly above last year's, but just in March, this is the March update, it has just joined last year's record. So what they wrote was 24 has about 50-50 or 59% chance of being warmer than last year, slightly better than a coin flip. The ultimate outcome will depend on the evolution of El Nino, which is part of the trigger for this extra warming, and the possible switch to a La Nina, that's the cooler phase later this year. And he also adds and variation in other regions or other causes as well, is what he meant to say. So this is really quite staggering. What does it mean for us in detail? From NOAA, they produce for coral bleaching, this is a different curve, it's coral bleaching, and tells you the very dark colours here tell you that regions have been up for 20, 16 weeks above the bleaching threshold. So what NOAA have done is to predict the bleaching thresholds for different regions of the world's ocean. And this was done this is April's prediction. So where you see these dark black colours here and the reds, that means that's all potential bleaching areas. So you can see the Great Barrier Reef, in particular, has been very susceptible to bleaching, and that's exactly what's been observed. And the Caribbean was extensively damaged. So this is an observation from the Great Keppel Islands, which is, I'll show you in a minute, just out there. And the prediction is this is the widest or most globally extensive coral bleaching crisis, and certainly the most extensive since 216, 217. And bleaching is when these look all nice and pretty, nice and white, but they're actually lost all their tissue and now on their death, they're now dying, right? And then go back in a few months, you'll see them covered in algae. Go back in a year and they'll all be just a pile of rubble. Here's a bit of a close-up of the above graph, and here's Australia, here's the Great Barrier Reef, and you can see way offshore there's some very, fortunately the reef's a bit further inshore, these are very extreme bleaching, and right inshore you'll see some black, very strong colours, and that Keppel Islands, for example, is one of those sites which tells you that that's experienced about 11, 12 weeks of bleaching. That's probably a death event. Now, if you just get something a few weeks, it might just bleach and then be able to recover. So how long it's been subject to these conditions is quite important. What about WA here? You see there's this band here of bleaching, which just misses our coast. And fortunately, there's no reefs out here till you get to Africa. And there's some cool water, which is probably represents the cyclonic conditions have cooled the coral, the waters. And actually, we tend to be generally out of phase with the Great Barrier Reef during El Niños. When the phase shifts to La Nina, then that's when WA gets, or the Ningaloo Reef can be susceptible. But fortunately, Ningaloo Reef is one of the least vulnerable reefs to this problem at the moment because it's so close to deeper water here. At least that's the theory. So that's what happens with bleaching. Now there's another thing been happening in the Antarctic, and this is the amount of sea ice that's. This is the sea ice here that's floating and fluctuates from summer to winter. Obviously, the sea ice diminishes in summer here, and then in winter it expands outwards. And this orange line is the mean line for the sea ice at this particular time of year, July 23, and you can see there's much less sea ice than there normally would be. And this is the 23 curve overall. It's way below the average, right? And this is the major concern. And it's been actually decreasing for the last 4 to 5 years. And I'll show you what 24 looks like. So 24 is the blue line now. It's actually doing slightly better than 23, but just joined the 23 line. This is March this year, and so maybe on the same trend. I'm not going to talk too much about, this is what I call a wild card in the climate change. The Antarctic is the big driver of climate change in the sense that a lot of deep water is formed when this ice fluctuates, and it drives the big ocean current systems. It also controls sea level a lot. If there's glaciers that are land-based, if they start to destabilise and go into the ocean, we know previously that's caused major sea level rises. So this is the wild card, and I'll show you how that can be part of this concept of a tipping point. So the question I raised is 23 this year or this last few years a tipping point in our climate system? Are we now in the midst of a major change, or is it part of what you might call a normal warming trend with El Nino fluctuation superimposed on it? Now, what's a tipping point? It's generally an irreversible, at least on human timescales, right? Now, over long timescales, things will come back to some level, but it could be a system that jumps and it just can't move back to the previous state very easily, often rapid change in our Earth system. And it's actually due to the energy imbalance between the anthropogenic CO2 emissions, and here's a cartoon showing emissions from the industry and so on, and that's sort of pushing down this scale, whereas the absorption of CO2, the natural ability of the Earth to take up these emissions, is being overwhelmed, if you like, okay? So the sinks here aren't able to keep up with the extra emissions, and this is causing extra CO2 in the atmosphere, and that's driving global warming. And then the warming can be feeding back and affecting the sinks, right, how good the sinks are, so you can get a feedback system as well. It can also be triggered so you can imagine you're on a balance, and once it starts to go, right, chunk, it's very hard to stop it. You're on this sort of knife edge almost. And it can be triggered by, e.g. El Nino events, because they bring up a lot of extra warm water that does warm in the Central Pacific. And we have an increasingly unstable system. But an example of a trigger of a tipping point is, as I mentioned, in the Antarctic. So this shows a cross section. This is a ice sheet in the Antarctic. It's grounded, and then hot warm water's coming up, eroding it. And this is the sea ice that I was showing you before, the extent of sea ice. So if the sea ice, we're now seeing this kind of shrink the sea ice, so that the ice shelf, if you like, that's holding back this kind of major glaciers is being diminished. But what happens is that if some of the grounded ice is released, it will actually increase sea level, right? It's only the melting of grounded ice does that. Once you increase the sea level, you can imagine that the force to release more ice, grounded ice, increases. So it sort of feeds back on itself and makes the process worse. So you can get so increasing sea level will cause further ice sheet collapse, and that's a positive feedback on the system, and then the whole thing can go, right, very quickly. And in fact, not shown here is that these grounding lines are usually have a reverse direction, and so once they go at one point, the whole thing is essentially only pinned at one point for many glaciers, and that is again another instability in the system. So this is what we're worried about. That we think that should take hundreds of years, but it could go faster. We're already seeing certainly centimetre changes in sea level in tens of years, if you like. And I can say where we are now, and in many parts of Perth, would be above sea level very quickly, and you can see all the evidence for this on looking around our coast. And actually at Rottnest Island there's beautiful examples of where, when this happened about 125,000 years ago, sea level went up about 4 or 5 metres, right? And so Perth's quite vulnerable. Okay, so I'm going to make the point that the time clock is running down for meaningful emission reductions. That'll be the overall theme. And we're going to see if... I'm not going to talk much more about the Antarctic, but that is kind of I use the word wild card, because we're gambling, right? We're playing a gambling business in what we're doing the experiment with CO2. We don't really know the outcomes, and so we're sort of making educated guesses, but remember there's sort of randomness and lack of understanding in detail of everything that's possible. It's our best guess, but we're literally gambling with our climate. So I'm going to show you now a kind of unique record that, as I mentioned, I didn't plan to do, find it. I should say I've been working on these organisms for a long time, because I know they're a great climate recorder. And this is an example here. There's a couple. They're about this size, and they're very, very dense calcium carbonate. And they grow very, very slowly. And these are in the Caribbean, off Puerto Rico. The guy is using rebreather diving techniques. He's down about 80 metres. It's not me. I was sitting on the shores waiting for him to come back up. And actually, as I mentioned, I was looking for another record that I know about climate is pH of the seawater, ocean acidification. And I never expected to get such a very nice strong record of temperature, and I'll explain a bit more about that. So there's myself, these are the Caribbean collaborators, and Julie Trotter, my partner, who's also involved in this work. So let's first go back off a little bit, look at the arguments why 1.5 versus 2 degrees were made so strongly in this, the motivation for having the Paris Agreement. And this shows some of the modelling that was done, looking at temperatures, this is the mean temperature at 1.5, and this is the 1.5 column you can see here. This is the mean temperature at 2 degrees, and this is the difference between them. And you can see the scales, all the red, are about 1.5 to 2 degrees. So obviously we know that a half degree increment would change, particularly the temperatures in the high polar areas, particularly the northern polar areas. But there's other parameters you can measure. Number of hot days, for example. This is 1.5. You might not look at too much of a dramatic difference there, but here you can see the difference between the 2 and the 1.5, that the number of hot days in a year could change by at least 10 to 15 in these darker red areas. And you can see the areas that'll be presumably most affected. It's not always obvious too. As you can see, Australia in part only gets 2 to 5 of these extra days for going up the extra half a degree. Now I'm going to make the argument here that we're not at 1.5, we're now at 2 degrees from my records. So the sort of argument I'm going to try and present is that we're probably in this regime here now within the uncertainties of the models that are making these predictions. Now, we'll come back to that issue in a moment. So this is the Paris Agreement that Christophe mentioned, and based on that kind of information coming to the community, it was realised some action's got to be really taken. So these are disastrous potential outcomes. I should go back and say that if this happened, there's been an estimate that's the cost of this would be about $40 trillion, right? It might cost us $20 trillion to remediate some of it, but there's a huge cost in accommodating this and any greater climate change. I won't go through all those details, but there is a huge dollar cost of this, and they've been estimated. So the decision was to keep surface temperatures well below 2 degrees, and a reference to this pre-industrial levels, which is quite critical, and pursue efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels. So the 1.5 was a pursue efforts kind of target. It wasn't a really fixed, it was a sort of ambition, nice to do, but it wasn't going to be the end of the Earth if that didn't make it. The 2 degrees, though, was well below 2 degrees, was kind of a very definite ambition. And it was, as I said, it was based a lot on many models and experience of what an extra half degree increment will do. So it does have a strong scientific basis. Just to let you know, just to be sure, a global average surface temperature is what it is the area averaged of sea surface temperatures. So the oceans make up about nearly or just over 68% of the surface. So that is how that's weighted, and they're measuring sea surface temperatures. That's the water temperature in the top 1 to 2 metres, right? Now, the land takes up about the remaining difference, is roughly a third, and the measurement there is land air temperatures at about 1.5 metres above the ground. And all that is obviously based on a lot of historic records for land temperature, no problem. What we're going to talk about here, the sea surface temperatures, and it's considered for the ice-free parts of the ocean, right? So where you have continual ice over an ocean, that's considered as land, right? And then as it retreats, it becomes ocean. So there is a little, but it's only a few % difference. It doesn't make much difference. Anyway, but the other critical point is pre-industrial levels. They were actually quite clever, I think, talking about the pre-industrial. They did not actually specify it at the time. Later, it took about 2018, I showed you one of the reports, when IPCC then said, we better have a proper time to do this referencing. And they looked at it, and there were very few good records for the pre-industrial. It's a really tough thing to do. And they said, well, the best we can do is between 1850 and 1900. There's a whole report written on it. And what I showed you previously came from that report. And they faced the dilemma that, okay, we know the temperatures quite well for the last 50, 60 years, no problem. But you go back to the early 1800s, late 1800s, I'll now show you it's not so easy to figure this out, right? But hang on, there's some sections I've now got to go through first before I get to that point. So what they did was to take, so this is to do with the anomaly business. So this is the ocean anomalies in purple, And they're normalised, in this case, to 1961, 1990, which this average date here, right? And that's that's a 0 point. So that's when you go look on Hadley, one of the centres, and get the data. You'll see the temperatures are given obviously as anomalies, not absolute temperature, because with the global temperature, it's very hard to get a total global temperature. So we're all talking about anomalies now, right? Not absolute. And so these anomalies to start with are pinned at this point, and you can see the land goes through. This is the land records of these symbols, and they all are forced to be the same here, and then they take their natural whatever trend they have, right? So you'll see that was chosen, these are reasonably modern. You can see that the land and the ocean agree here, right? The land departs more recently. That's a very interesting thing. We'll maybe get a chance to talk about it. But actually, this is the pre-industrial period. You'll see the ocean and the land depart from each other quite measurably. So let me just think, I have to go. So then what they did was to say, okay, we're going to have 1850, 1900 as the pre-industrial. That means, of course, the land and the ocean have to have the same zero anomaly, right? So they then forced these differences here they removed them by normalising to this point. So they then made the land and the oceans agree for this time period, because that's what a pre-industrial is defined as. It's a period of stable temperature, and the land and the oceans have to be in some sort of equilibrium. They can't be different. But the trouble is, when they forced the land to be the same as the ocean, of course they forced the land up, right? And its anomaly jumped up further, and you see now the land is always above the oceans. And so in the Nature paper that I wrote, and I was trying to get more evidence for my work, which I'll describe in a moment, I said, well, this is weird. You cannot. Why is it that the land suddenly becomes warmer immediately you start the industrial period? Because there's no sudden magical forcing agent to do it. It's a gradual forcing agent. And it's actually led to some misinterpretation about land temperatures as being always warmer than the ocean. That actually is not really, the anomalies, it's not really a natural consequence. Until you have different conditions, there's something different changes, like a tipping point. And also when you look at the ocean record a little bit, you see there's the ocean record again. So this is ship-based, I'll show you that in a moment. These records here are actually warmer than the ones in the early 1900s. You'll see that for some reason those SSTs there are warmer than the subsequent ones, which has made this and so this is the so-called global, well, I'll now show it. The orange then is the average of those two, given by those proportions that I described previously. 1/3 land, 2/3 ocean, and this is what everyone looks at as the global warming trend. So I raised the question, well, maybe there's a bit of a problem about how that's been derived. It's not quite legitimate. But anyway, and only this insight only came from my looking at my own data, I should say. So there's a question mark over it. Actually, interestingly, oops, I think I might have run out of juice here. It's all right. Interestingly, is this going to work? Okay, this is pretty weak. Interestingly, if you look at this orange record, you'll see that it really does, and there's the 0 point, right? It's all forced to be 0 along here, 1850 to 1900. It doesn't really move much above 0 till about 1960, right? So it's really delayed global warming quite a lot, I think. And I was always wondered as a student, how come global warming was so delayed when we know we had anthropogenic CO2 happening much earlier? And actually the standard explanation was it's all this is natural variability, but then it looks like this natural variability doesn't continue to the recent record. So there's some, again, you can look at it, there's a few question marks. So I should say there's absolutely no question that we've got global warming. By the way, I'm now arguing about a detail about the history of it, but as I point out, this can be quite profound in what it means. Now let's talk about another factor we have to think about, and it sort of supports my argument about why you've got to be careful how you look at the land and the ocean records, because the ocean is important because all this blue here is ocean, and this is heat uptake. So this is how much of the heat that's been produced by the CO2, where's it gone? Some is left in the atmosphere, giving us global warming. Most of it, 90% of it, has been taken up by the oceans. This is the dates. So this is about 1980, I think, somewhere here. You can see it. And it rises up. We're now in the year 2020 here. So this is only the last 50 years. And you can see this light colour is the shallower 0 to 700, or the very top, this bit is the top 300 metres, which I'll tell you is very important as well. But you can see the ocean is the big boy in the heat uptake. It takes up 90% of the heat, right? So you cannot escape the forcing, the performance of the upper ocean in taking up the heat is going to control eventually, the temperature response of the globe to the CO2 forcing, right, in a way. There's only the dynamics between the ocean and land that we don't quite get right all the time. So you can't have something like, you can't say, like at the beginning, at this point here, at the beginning of 1900, you cannot really have the land way warmer than the ocean and staying that way, because the ocean's got the heat content, and the land is only this little bit of brown stuff down here, a few percent. So it's no way that it can by itself control the system. The ocean, we're in the right place, the marine centre here. The oceans are the ultimate player in the game. And in fact, if they were a little bit more efficient, we wouldn't have to worry so much about climate change. But it's because they're a little bit inefficient that the residual heat is staying in the land, or building up in the atmosphere and land. So that's an important. So we have this sort of dilemma, that global warming considers still 70% oceans, but actually it's taking 90% of the heat. And there's another issue with carbonates as well. So that's an important overriding thing to remember. So anyway, continue on with the story, not to be put off. So how do they measure these temperatures, the sailors? Well, they'd throw a bucket over the ship, right, on the side. They'd pull it up and dip a thermometer into it, and they'd go off and write down the temperature measurements. We need to go back a few.
Yeah, I might just let you navigate to it.
Yeah. And remember, these measurements were mainly meant to give the shipping companies some idea of... here we are, whoops. They're meant to give the shipping companies some idea of, when to send out their sailing ships, as shown there. And there's a nice paper in little letters in Science describing some of the issues. And you can see the tracks, right, that in 1800 there are ships, actually some going off to the East Indies, right? I got it right. And then, of course, there's North America, Europe, later, they're all... And then actually this trade diminishes a little bit, and you can see the tracks with time. So that's where, obviously, they're only measuring temperatures where the ships were. They barely covered the southern hemisphere. The Pacific, in particular, was very poorly recorded. And my view a bit is that the Pacific is where the El Niños occur, and they missed the variability from El Niños up till 1900s at least. They picked up some of it, but got the amplitudes wrong and got the temperatures wrong. And you don't have to be very far out. If you miss the warm pool, or if you stay in the warm pool too long, you can easily get 0.4 degree error for that year, right? So it's not, and the records are generally so bad they don't go beyond 1850. So they're talking, so this is a problem. It's their problem, but this is an explanation for why I think I'll show you a major difference between what's been observed with the ships, with throwing buckets over the water, the sailor going off and having it. They pull up the bucket, usually a canvas bucket. If he went off and had a little smoko, or didn't measure the temperature exactly right, or if the wind was blowing a little bit more, right, you could get easily half a degree effects. So it's very hard to measure using such primitive techniques. So what we did anyway, we're off Puerto Rico, which I showed you. And what we did was get these guys come from deeper water, from about 30 to 90 metres, and they're 300 to 400 years old. We're going to move on. And they're within what we call the mixed layer, which is deeper, but it's well mixed by winds and other convective motion. So the average temperature is equivalent to the sea surface. If it mixes, it's a good average temperature. It misses out a little bit on that very hot, thin layer on top, which you know if you go for a swim on cold days, on windless days, you'll notice the very top the skin effect can be quite anomalous. It's well mixed, it gives you the best records. But of course the sailors didn't want to throw their buckets too deep, so the records never have this, right? So it's a kind of unique record, but we now recognise if you're doing it again, this is where you'd measure the temperatures from. So these are the specimens, and we can date, there's our collaborators. They came back alive from their deep rebreather diving, which is pretty amazing stuff, actually, I should say. And we have facilities at UWA where we can date these objects very accurately using what's called uranium series dating. And we can date, we go down, and the object is growing upwards from there. This is the outer living, so it gets older and older as you go down. So we can precisely date where we are in that specimen. And we had half a dozen of these specimens. And I went off and did the geochemistry here, showing strontium calcium measurements and ages. So the ages go from, we did this work in about 217, and you have to miss a little it's up here is better. And you can see they each make subparallel arrays back to 1700. There's 300 years of record in that little object, and we've got about half a dozen of them, so we've got good replication. And it turns out, this is the anomaly business again, that you can see they're offset. Now we think there's a slight gradient in temperature in the mixed layer, not very much, but there's also what's called vital effects. Now normally these vital effects, these are the organism itself can do a few little offsets, right? Actually the strontium calcium ratio gets offset slightly by the way the biology works slightly. But it looks like, because they're subparallel, it looks like it's constant. For corals, they tend not to be constant, so that's one problem with regular corals. For these objects, they're very primitive actually. They don't have, I won't go too much into detail, they don't have zooxanthellae, for example, and they're very ancient. They've been around for hundreds of millions of years and survived. So they've got their own inbuilt ways to deal with climate change almost. And they live where there's no light, right? They live in these deep waters. So that's the explanation. So when you join up, what I did was make anomalies, right, by normalising all these ratios to 1961, 1990, the same as the temperature records. I chose that to be matching up with the temperature records. And you can see they make a beautiful array. They all join up. This one's a little slightly off, but it's not too bad. Going back, and this is the array of which I will show you later, I believe is the global warming array. Actually, CO2 I've shown here just for interest. We know that CO2 started to increase probably about 1780, certainly by 1800. You can see it clearly. And by 1900, it's way above the baseline. So we know definitely there's got to be some global warming happening during that period, right? So, these are the Law Dome records, exquisite records from ice cores. And I use Cape Grim as my record because it's not because it's just CSIRO, but it's actually a low variability record. It gives you very nice annual numbers to play with. Okay, so that's the record. So I had to do a calibration to say, okay, I've got these strontium calcium ratios. I know from my previous work and everyone's else that the incorporation of strontium into the carbonate is temperature dependent. We know that, there's been experiments done, so it's really well-based, and it can go through the detail how strontium gets incorporated into that aragonite structure, and it's got a temperature dependence. And so this thermometer, this proxy, is strongly physically based as a temperature proxy. It's not anything else, right? It's just one thing that's doing it. with a little bit of minor biology as the organism modifies its calcifying fluid slightly. So what I did was, actually I couldn't find a good record above surface to use. I looked around, and the best record I could find was that using the global SSTs, which are shown in these purple symbols here. And then on the other axis, I just plotted the ratios, right? And you see they overlap perfectly. And so when you make a plot of the global, like we use the Hadley, this is the Hadley Centre SST anomalies for the global versus the compiled strontium calcium ratios for each. I did it at 2-year intervals. That was what we worked at. You see there's an excellent correlation of about 0.91, with the main problem being actually ENSO events in the record of the Hadley Centre. So there's an empirical evidence that this record now follows the global sea surface temperatures, which I was surprised about. It took me about a year to figure this out. I didn't believe it, right? And I was doing all the different things we do as geochemists, but we couldn't. This was by far the best explanation. And then I came across a paper where they're looking at what's called the AMOC, which is this circulation of different water masses in the Atlantic. This overturning circulation in the Atlantic is what the symbol words mean. And it causes warming, for example, up in North Atlantic, this circulation is actually one of the critical. It's being generated down in the Antarctic by production of deep waters, and these deep waters are flowing up, and then there's another compensating trail of surface waters here, which makes this circulation and makes the climate of Europe nice and all the rest of it, but it's quite vulnerable to change. But anyway, they've run models saying, well, if we double CO2, what will this, if it exactly follows the atmospheric CO2, it'll be white, and that's what the Caribbean does. So the models were showing that, the central equatorial area was least sensitive to these anomalous or changes in circulation, and they're actually sensing the surface waters coming right across the Atlantic and up and finally sinking down in the northern part of the Atlantic. So those waters that go through the Caribbean in its mixed layer are transiting for a long period across the top surface and soaking up all the, seeing the whole atmospheric signal, right? And as I'll show you, those temperatures can be, temperature changes in that region are very, very sensitive to global changes. So this is the record, and you'll notice, just to prove it, there's a dip here about the early 1800s, and this big volcanic eruptions went off. That's in Tambora in 1815, and we can see that in these Caribbean records. This is the Hadley IPCC, what's using their temperatures at this time. And you can see my record has it's flat after, from all the way backwards. It's got this dip you have to avoid because we know volcanism is transient, so you have to avoid that. So the baseline, so this is the baseline I'm using, right? And there's a major offset with these Hadley data, which are the warm ones. They are warmer than the subsequent period. And that difference actually is about 0.7 degrees. It's quite large initially and then diminishes, right? And I have a consistent pattern of increasing temperature from about 1860. So the start of the industrial period, we now believe the strong evidence is 1860, and here's this warming going all the way up. And after about 1960, the records are indistinguishable. They overlap, in part because I did the calibration to fit it at the one point, right, at the 1961, 1990 average. They have to fit at that 1975. They can have different angles though. So I thought, well, that's pretty neat. So I've now got another separate record of global warming. No one else has this. Isn't this neat? What can you think about? So the next thing I did was, actually I didn't do this right away, but I thought I've done my bit, I'll send it off for publication, da da da. But then the people said, I got these kind of, prove it. You need another thing to prove it. It turned out, I then discovered this land temperature business. And so here's all the land temperatures that I've been talking about already, right? So these are independently measured by thousands of thermometers around the world. They've compiled all the temperatures. There's millions of data points in this, right? And lo and behold, you'll see the land temperatures agree very well through this period from 1860 to 1900. Of course, they agree quite well through here, and they still have this offset up there. But as you go further back in time, they show this huge dip during the volcanic eruptions, of course. Major cooling when the volcanoes, when Tambora went off, that was a year without a summer, right? I think it was so cool. All the potato crops lost in Ireland. There's a huge human catastrophes. And I'll show you that. I'll show you the result of that. So this is again the same record. There's mine. There's the land. There's the what I call the IPCC record. And I've now resolved this conundrum. We've got the land basically following the oceans, apart from particular events like ENSO events. So I've resolved one problem that was in the original IPCC, and have supporting evidence. The land records, what I'm saying is the land records support my ocean record, as they should. That's how things are. And the only difference is this is a natural baseline. Now, I've now switched, I'll go back. This is just my quick switch in. The anomalies were initially at 0, this 75. Then I added an extra 0.9 to bring the 0 down to through here. So this is now the 0 point around 1700 to 1860. And then you'll see from then on, the numbers tell you the amount of global warming from the baseline. And then I just did the natural, the easy thing of, to get the global warming, you have to just average the land and the ocean, and that dark red colours are then the global warming. And this is the baseline, and you can see the volcanic eruptions in the baseline. There's actually, turns out there's Tambora, there's an 1809, there's an unknown, and then there's some volcanoes went off around 1830 that also influenced temperatures. And so these combined records show my ocean plus the atmosphere, and that's what I think is now the global warming, the best global warming record, which I'll make other arguments, is very consistent with what we would expect. Okay, there's a little bit of minor diversion just to give you some background about the next steps. This is talking about emissions, right? So this is how we think about emissions. So you can measure them annually. So this shows grey is fossil fuel. This colour's land use. Then on the other side, so these are all the emissions, that E, right? On the other side of the ledger, you have the sinks, what the sinks are doing, the ocean. This is with respect, I should say, to CO2, carbon. This is land and the atmosphere. Now, this is what we call the cumulative emissions, that you keep adding them up, i.e. that this is the total amount of fossil fuels ever emitted, right, since industrialisation. And it's a nice smooth record, and this is the land use emissions. And if you do it, you can do it annually, but they're jagged, right? These numbers are much smaller. You'll see some of these later. So the cumulative effects of E is the total amount from there, E, which is fossil fuel plus land use, add them together, they're the total amount of emissions released since the industrial period, right? So that's called E. And you can see that, in essence, that's the major bit of global forcing. And the forcing comes from stuff that doesn't end up in the ocean. I mean, the oceans and the land take up the CO2, and the atmosphere is then blue, right? That's where the additional amount of CO2 is going, and that's what causes the atmosphere to increase in concentration. And you can then see this is the amount from about 280 ppm to start with to about over 420 now. That's the total. So there's a thing called cumulative emissions, E. That's a simple concept, I think. By the way, so with CO2, an important number is how much has gone into the atmosphere. I call that A, and the ratio of A to E is called the airborne fraction. That is the fraction of emissions, total emissions released, that now reside in the atmosphere. So that's a nice parameter to have, actually, because the question is how well does that remain constant? Because it reflects the stability of the sinks. So that's just sort of a bit of basic stuff. So it turns out, I'll show you the evidence a bit later, that let's go first with the cumulative emissions. If you plot the total amount of emissions versus my global warming record, you'll see that's the red line. That's in E is red, right? They follow perfectly almost. And this is an outcome from actually modelling, not from, I'm not the first person to do this. The modellers told us we should do it. Of course, we know that warming should actually follow the amount of, the blue is the, actually this blue is the amount of atmospheric CO2. It follows pretty closely as well. So as you add, you know, the atmosphere is the forcer, so you'd expect the amount of CO2 in the atmosphere to be the main driver. But there's some other complications in the system that, in particular variations in this airborne fraction, that can confuse these models, you know, can give you a different result from a linear, you know, from a one-to-one fit. And it turns out that the cumulative emissions fit is better than the atmosphere fit. But they're both very good, right? But let's go to the next. So you've got the concept what a cumulative emission is, right? That's just the sum of them. That's pretty straightforward. And so this is then the model results. They took models. Here's the cumulative emissions, and then they plotted temperatures off their models, and they found always these straight lines going up, right? I.e. directly, so that temperatures in the models are directly proportional to cumulative emissions. And it's a very, very simple piece of arithmetic. So simple that the modellers are still arguing about why it works so well. But actually it never worked very well for observations. So the actual orange is the previous observations using the Hadley. And you see the problem is way down here at the low emissions end, you've got all this sort of odd signal because they've got the sea surface temperature wrong. But the last bit from 1960 agrees very well with what I have, right? So there's now a new thing called transient climate response to cumulative emissions, which is the temperature, the slope of these arrays, right? Basically, it's the gradient. And that if you know what that slope is, you can predict the Earth's temperature directly dependent on emissions. Straightforward, right? The only problem with the models, they differ. Right? They differ from a sensitivity of, now it's usually measured with respect to 1,000, actually I used the terminology gigatons of carbon. There's 1,000, or if you want to be smart, you can use petagrams. That's a decimal or a different 10 to the 15th grams. Anyway, the range of these slopes makes the sensitivity just over 1 to about 1 or about 2.5. So the models don't have the one number. They have a variability, huge variability actually, but they cannot escape. They always get these straight arrays way up to super amounts of CO2 even. And they've run these models back and forth looking at a whole lots of different things. So this is a now robust, from the modeller's viewpoint, a robust finding. And if it had come from us imperialists looking at real records, they wouldn't have believed it. But it came out of their models, so we all are happy, right? And now I've got a record, which I'll now show you. I'll just point out that there's a difference between the red and the orange is the difference in global warming. It's about 0.5 degree, which I find. So this is, the red is my record, right? And it gives this sensitivity at 1,000 gigatons, which is, we're coming very close to actually. So there's 1,000 gigatons of carbon emissions in total. We're about here, we're just over 700 going up. This is the red going up, chung, chung, chung. You can see all the interesting periods. Here's 23, 16, da, da, da. And we're marching up. And here's the 1.5, we passed it already. There's 2 degrees. and there's 2.5. And this is a dead straight line, and you can look at the deviations from the straight line, and it's incredibly minimal. It's less than a 10th degree. That shows a 10th of the degree there's one standard deviation. And you can see there's the different years, the different El Nino events, way back to 1878. And there's the opposite La Nina phase. So this straight line, it's in the literature. I mean, it's been used a lot, but not for actual observations, because the observations weren't only recently make a bit of sense, and it's never been able to push back as far as what I've done. So my argument then now is, look, my new record, it makes sense, and it actually agrees with the emissions that we see. So therefore, it should have, it's quite viable. Actually, there's another implication that when I made this plot just a few days ago, you'll see that if there's a major disturbance in the system, it should depart from linearity, right? If there's a major tipping point or something's happening, we'd no longer expect this to hold, right? Because it depends on the strength of the sinks. It would tell you that the ocean sink is changing and or the relative relationship between CO2 being stored in the land and the ocean has changed, right? Because how emissions are stored is quite critical. It's the total emissions, and then we've got to get it's the residual that goes into the atmosphere, which is still quite high. It's over, remember the airborne fraction is about 40%. So if that airborne fraction changes, it'll also change the relationship. So it's got built into it already these kind of requirements. And actually the modelers can't figure out yet why it's so good. But, and now it looks like my observations are more precise than the model estimates by about a factor of 5. So instead of having this large variation, we've got the 2.4 pinned down to about a 10th degree, which is what I show as the variation at that 1 sigma level. So it's an argument, one argument I'll say, that we haven't crossed into a new phase yet, because you look at where 23 is on this plot, it doesn't look overly abnormal, right? In fact, if you go back to 1878, you can see one's even higher. But that is almost certainly wrong, because they never had ships measuring it properly, because you couldn't do these are global numbers, right? So anyway, it's another criteria. So now let's look at the future projections, what we can do with it. So this then shows what we call the annual emissions per year, right? Which was the left-hand plot I showed you on that other diagram. And we're looking at carbon. How much carbon's been emitted per year. And you'll see it's a number around 8 to 9, been going up steadily since 2000. There's a little decrease here, and that turns out to be about half a gigaton, and that's during COVID 2019, 2020. I'll show you that. And then it goes on, and this is a prediction from the curve of what I've derived, right? And then you can ask the question, well, can we get down? How can we? Well, I'll add the next plot actually to show you. Let me just remember. I'll show this now actually. So this is the temperatures shown as well, right? So if you want to be on curve C, that'll take you to 2 degrees. So if you wanted to get down to 0 emissions and have less than 2 degrees warming, you'd have to go down this green curve, which is almost a steep drop. You'd have to have huge emission reductions, because we're so far away from, this is the distance we're away from, we're about 10 gigatons per year away from 0 emissions. So you'd have to do at least 2 gigatons a year to get down to 0, and you probably wouldn't make, the 2 degrees is, I think, almost impossible to make, right? You can actually, if we start pretty soon, you can, at half a gigaton per year, you can get down to 0 emissions by 2050, and I predict that the temperature should only have risen by then about 2.2 degrees. So that's probably a plausible thing we can do, assuming that you can do half a gigaton per year. These are some words written by one of the people who've done a lot of work on this using cumulative emissions, and it gives you some general things, that if you want to stabilise temperatures, you need to get to net zero and average and stay at net zero forever, and then the temperatures will essentially, in human timescale, stay forever at that point. If we could have got to 2 degrees, would have saved us a lot of money and trouble, probably tens of trillions of dollars. I think the best we can do if we start pretty soon, is end up at 2.2. And because you can't get CO2 out of the system, out of the atmosphere, we're going to have to live with it for a long, long time until we get fusion reactors going and can actually figure out ways to sequester CO2 out of the atmosphere. But that's now impossible, practically impossible, I'll use those words. And by the way, these projections depend on no delay or regime. Well, if you have a delay, okay, if you say, we'll do it next year, don't worry, we'll do it 2030. We'll start 2040. Every time you delay, to get to net zero, you've got to go down by 2050. You've got to go at a steeper and steeper, more impossible rate. And so obviously, the sooner you do it, the better. And hey, if we'd started back in the year 2000, we could have easily got down to the 2 degree limit if we'd done modest half gigaton per year emission reductions. Now, how practical is half a gigaton? What's a gigaton, right? It's a sort of number I'm throwing at. It's 10 to the 9th tonnes, right? It's a big number. But what does it really mean? So let's just ask that, and can we practically think about a number? Is that a practical number to think about? Well, actually, it's not. Australia's total emissions back in 2020-21 were about 0.125 gigatons of carbon per year, a tenth of, not. I'm only asking that we reduce emissions by half our currently annual amounts. If the world did that, we would be not so. But it turned out there were bushfires in 2019-20. This is the bushfires in New South Wales, and you can see all the smoke and stuff. And someone went and figured out how many gigatons of carbon was emitted in those. It was actually about 0.25 gigatons of carbon was emitted during those bushfire periods, right? And it turned out that if you go back, remember I said that during COVID we actually saved that 0.5 gigatons. We just need COVIDs every year. We're home and hose, right? But the trouble is, this shows the problem with the environment. Those bushfires, they took care. They used half that extra. They took up half the savings, right? Our bushfires in Australia used up half the global COVID savings, right? So we've got to make sure we don't have bushfires and other catastrophes. Otherwise, emission reductions can get very, very difficult. So there's Australian bushfires accounted for 0.25 gigatons during this period, and they where does it say? And global. So the annual reductions. Anyway, certainly annual reductions of 0.5. This shows all the budget for 2019 to 2020, and this shows 2019 we're about 9.6. 2020 we're half a gigaton less. This shows all the reductions by the different countries, and then Australia went and had our bushfires and lost half of that, right? So anyway, that's the story. So the point being that I believe that if we can do this during COVID, there's no reason with concerted effort that it's got to be a global reduction of 0.5. We cannot have bushfires going off anywhere else. We can't have someone else emitting stuff somewhere. We can get down to half a gigaton, I think, per year, and we have to do it for the next 25 years, and then keep emissions zero for thereafter. So that's I'll come to the conclusions now. So the record, I think I may try to convince you that I think there's no question that the industrial era commenced in the early 1860s. That's obvious from history, obvious from the CO2 we observe in the atmosphere. So that shouldn't be a big surprise, but IPCC don't like it. The temperatures were that I get are half a degree warmer than the IPCC, right? And because of their error in the ocean record. And so now I think we're about 1.9, and the Paris Agreement we passed in that period. So this is just talking about this, there is an argument, a weakness. You might say, well, why don't you have multiple examples of what I've just shown you, right? Wouldn't it be great if I could line up in every ocean the same kind of record? And so the reviewers say, well, you should actually have multiple records like this. Well, it turns out it's very difficult to do. Only took me about a decade to do. And of course, the SSTs they're using for this period, they don't have multiple examples of them. They just have these skinny ship tracks that with drunken sailors measured mostly at the time, right? So anyway, less than 2 degrees I think is virtually impossible, as you need very large emissions. 0.5 gigatons per year, I think, will end up about maybe around 2.3 with achievable by 2050. Delays will increase the emissions required. The question about this now is, are we in a tipping point? And what's happening, right? So this warming is due to very strong El Nino with on-trend global warming, right? So that global warming is going as predicted, right? And this is the new normal, right? So this kind of period we're now facing, I think, get used to it. Every time there's an El Nino, you should expect this kind of warming. This is the standard stuff, and it's going to get worse with time, right? And global, because we know they closely track emissions, and emissions are still going up, which I showed you. But tipping point change cannot be excluded, and ongoing melting of the Antarctic sea ice, and there's also warming in the North Atlantic that looks like it's connected with the AMOC. That Atlantic circulation may be given up the ghost. It might be, its driver is having a tough time down in the Antarctic, and some things happening. So the wild cards, they could play a major role, and we'll find, in retrospect, we'll find out, particularly I think the Antarctic is a big problem. And so far I can't point to end of the earth, but things aren't looking good, but we can save it, right? 0.5 gigaton per year for the next 25 years, actually it's 4, I think it's 2 bushfires of Australia type savings on emissions will do the trick. So I'll leave it at that.